All right, so hello and welcome to our one class session for this morning. Again, my name is Joey. I'm going to be your mathematics and chemistry teacher for this session. Specifically for today, what we're going to do is, again, we're going to explore and kind of answer your questions about regarding specifically towards math. Both today at the if you're tuning in from the Eastern time, it's at the 10 a.m. Eastern slot, and also at the noon slot as well if you're in the Eastern time. So I'm going to be doing two sessions today. So primarily what I'm going to do is for the first hour, I'm going to focus on primarily if you're coming from Canada, maybe the grade 9, maybe beginning of grade 10 curriculum for the first hour. And then for the second hour, it'd be for mostly the grade 10 curriculum. And then if you're tuning in from the US, that would mean for this first hour, I'm probably going to do a bit of like pre-algebra and geometry. And then the second hour, probably more so the later parts of algebra 1 and algebra 2 as well. So these questions are, again, sent in by you folks at home, you students at home, or honestly, anybody from around the world. We've collected a frequently asked questions for both topics in secondary school math and in chemistry, as well as higher level maths in the college and university level as well. So that's kind of what we're doing for our stream for today. What we're going to do is we're going to take this next hour, we're going to answer some of these frequently asked questions in those particular subjects, and I'm going to try to walk you through my thought process as I'm answering this question, and together we're going to verify our solutions that are provided on the OneClass website as well. But what we're going to do is we are going to verify that the solutions are correct and incorrect using our logic here. So again, if you're tuning in for the first time, thanks for tuning in. Again, my name is Joey. I currently come from a background of being a secondary school teacher, particularly in the subjects of chemistry and math and mathematics as well. And I also teach music. So that's kind of my background. And I'm residing in Ontario. So I'm familiar with the Ontario curriculum, but I'm going to familiarize myself with the U.S. curriculum as well. So you folks in down in the States there can kind of like help and can kind of help follow along while I'm doing this. So I'm going to try to relate it back to the terms you know as well. So without further ado, let's get started. Again, I have a set of 10 questions for us for today. So if you're tuning in for the first time, again, wave hi in the chat, and I'll be sure to be more than happy to kind of answer your questions here. So let's get started. So what we have here is we have this first question, right? It says here, this is number 1. It says, which teacher exhibited the most variable year-to-year performance over this 5-year span? And again, I think I don't know, I can't see the graph per se in this graph, per se in this question, but when we talk about variability and year-to-year performance, so I'm going to assume that the graph looked something like this. So it's going to have an X and Y axis, so I'm going to draw that out for you. So it has some x-axis and some y-axis. And it says which teacher exhibited the most year-to-year performance. So when we talk about year-to-year performance, it means that our y-axis here is performance, right? So I'm going to say P for performance, and X here would be in terms of time, right? As you can see in my solution here, this student coming from the University of Waterloo, there's years here, right? So I'm assuming that my independent variable is time, and it's in years, right? So that's going to be my two axes here. And then what they did was they graphed out something, right? There was some term of some sort of graph that described each teacher, right? So there was Jill, Ed, Ralph, Tina, and Sam. So there's 5 different functions or graphs that are in this axis, right? So let's say I'm not going to draw it up because I don't know what the graph actually says, but I'm going to say that there are 5 functions. So I'm going to say that there's Jill's function. So there's Jill, there's Ed, there's Ralph, Tina, and Sam. So there are 5 different functions, and what it is, and I'm going to show you an example. What this means is that it's to describe their specific variability. So actually, let me erase these names, and maybe I'll write these names over here. So this would describe Jill, Ed, Ralph, Tina and Sam. And what it is for example, what if I don't have the graph here, but if I drew, for example, like a straight horizontal line representing my function, what would this mean? So again, take a few minutes, or take a minute. If you're in the chat, let me know what do you think about this answer. If I drew a horizontal line for in this type of graph, what would that mean for the teacher? For example, this is person A. What would that mean? So take a minute to think about that, and then we'll reconvene and we'll answer this question here. So we only have a horizontal line for person A here, a horizontal line. What would that mean in terms of our function? A lot of you might default to say, oh, this is zero slope. It doesn't really say anything, but I encourage you to extend your thinking besides that. Remember, we're talking in terms of time and years and talking about performance, right? This is our performance in our y-axis. And this is from 05 to 09. So let me say this can be 2005, 2006, 2007, 2008, and 2009. Something like that. So if I had this looking function here, it means that my performance stayed the same throughout the years, right? So this would mean that performance was constant. So constant throughout. I'll just say constant. Constant in terms of no change. There's no change in performance here. Okay, sweet. So if there's no change, then what if I had something like this? What if I had something like that? My red graph here. What would that mean? So if the A and this, let's say this is person B, right? So again, if A was constant, there's no change. This B here, if you analyze this line here, there is some sort of slope, right? And there's some sort of slope. Again, you can relate it back to rise over run. You can relate it back to, oh, there's a change in something, right? And as you can see, it's increasing, right? There's a change in performance, right? So I can say here that this person B is constantly improving, right? There's a change in performance. Or I can say linear increase in performance would be in the red. And what if I had something that, let me graph this black line here. What if I had something like this? What if it started off like what if it started here, and what if it did like a little dip here, and then he would maybe come back to normal? What would that mean? And again, this here, again, I could do in terms of, I could do a rise over run, but as you can see, you see a curve in this graph, and a curve in this graph means that there isn't a linear, it's not linear in this case. In this case, there's some type of function or some type of there's difference in slope every single point in my performance. So 05 has a different slope than 06, 07, 08, and 09. Whereas for my red graph here, it was the same linear increase, which means this one here would mean it would be the most variable. Or when we say most variable, we mean that the most changes in performance. So most variable / most change here. So when we talk about which teacher exhibited the most variable year-to-year performance over this 5-year span, we're looking specifically at this black chart here. Why don't we we're looking at this black function here, not the red function, not the blue one here, but this black function here. It says the most variable and the most change, right? So as you could tell from the answers here, I'm gonna assume that this is correct here because I can't see the graph. But as you can see, Jill's performance was the same throughout 2000 and 2007, and her performance gradually increased. So maybe it would have been something like 05 to 07 would have been like, oh, it was. Let me draw another graph here this one would be for Jill. So I would have something like, if it was constant from 05 to 07, be constant, and then it would gradually increase, right? So maybe like a gradual increase or something like that. And this would have been 2005, and this is 2007. This here's my performance. This here's in years, and this would have been for Jill, right? This would be Jill. So that's what that would be something like that. And we're talking about Ed here. Ed's performance was never constant and it always varied in time. So never constant means that it's most variable, or there's most change. So as you can see from this curve here, it's never constant, right? I'm going from here, and the difference between '05 and '06 was different. '05 to '06, or '06 to '07 was a huge dip. '07 to '08 was an increase, and then it flattened off, right? So again, this most variable is most change here. So the answer here is actually Ed. But we'll look at the other options here. Ralph's performance was constant during '06 and '07 and '08 and '09. So when we're talking about constant performance, it's again this line, right? I just have this line here. It's a horizontal line indicating that it's a constant performance. Cheetah's performance was also constant. Sam's performance was also constant. So again, it's these horizontal lines here, right? Horizontal lines for those I guess teachers in this case. So that's kind of our solution here. I'm going to verify the solution and say great solution. I can't great solution, but I couldn't see the graph. But I couldn't see the graph to verify if graph stated that Ed had the most variability. So I'm going to say that. So that's going to be my solution here. I'm going to say that the solution is correct here. So again, we're talking about functions. We're talking about variability and constant in terms of slope, and constant in terms of, and variability in terms of change in slope. So that's kind of our concept here. So my solution is correct. That's awesome. Okay. So next question here. This is question 2. So if you triple 4 and subtract 2 each day, how many days until you have 0? Okay. So it says here, if you triple 4, so if you triple 4 and subtract 2 each day, how many days until you have 0? Okay. So again, this classic algebra problem in the grade 9 or grade or pre-algebra in the algebra 1 level. So it says here, if you triple 4 and subtract 2 each day, how many days until you have 0? So again, what we have to do is we have to create some sort of let statement. So let's say let's actually let me give you a minute. If you're in the chat, let me know if you're in the chat, and let's actually work through this problem together. So maybe I'll take a minute, think about this problem. How would we solve this problem? And there's a hint here because I have the solution here, but I encourage you to again kind of maybe read over the solution and see if the logic is sound here, but also kind of work this on your own. So maybe take a minute to do that. So let's do it. So again, here, if you triple 4 and subtract 2 each day, how many days until you have 0? So let's say that we're going to let some variable because we have to solve for the number of days, right? So let x, or any other letter here, let x be the number of days, because that's what we're doing, right? We're solving for this unknown here. That's cool. Okay, so we have our let statement here. So now we have to organize our words into mathematical expressions, right? So it's here, if you triple 4 and subtract 2 each day. So if you triple 4, tripling 4 just means what? You're doing 3 times 4, right? Triple 4 here means 3 times 4, which means 3 times 4 equals 12 here, right? So we have that. That's our first kind of statement here. And subtract 2 each day. So if we're subtracting 2 each day, then what we have is that we are going to do some sort of it's going to be you're subtracting 2 per day, right? So and you have, if x is equal to the number of days, then we would have some sort of function where it says here we have a triple 4 and we're subtracting. So we have this number 12 here, and we're subtracting 2 each day. So when it says 2 each day and x is number of days, then we would have to have 2 times x, right? Time multiplied by x, right? Because remember, x is the number of days, and we're subtracting 2 each day. So the first day I would subtract 2, the second day I would subtract 4, third day I would subtract 6. That entire function or that entire expression can be modeled as 2 times the amount of days, right? So we have this here, 12 minus x. And how many days until you have 0? Then you have to equate this or make the equation that states that this would have to equal 0, right? So that's going to be my algebraic expression here. What we can do is now we can actually solve for this expression, right? So in order for us to do that, what we can do is we can isolate our variable here. So what we're going to do is I'm going to move the x to the other side to make it, to isolate it, right? Because I want variables on one side, right? So let's do that. So I have here, this is 12 minus 2x. If I move minus 2x to the other side, I'm going to do the opposite operation and add both sides by 2x, right? So I'm going to have 12 equals, and this cancels out on the left side. So I'm going to have, instead of minus 2x, I'm going to have positive 2x, right? So 12 equals 2x. And then what we're going to do is I have 2x here. I want to get x alone by itself, and it's 2 times x. So I'm going to do the opposite operation and divide, right? So I'm going to divide both sides by 12, which means 12 divided by 2 equals, and then 2x divided by 2. These two just cancel out, right? So I'm just going to be left with here x would equal 12 divided by 2 is 6. So that's going to be our answer, right? So our answer here is, and if I were to create a statement, and it's going to say that it will take 6 days till we get 0 or something like that. So that's going to be our statement for this question here. That looks like an H. Yeah, it will take 6 days until we hit 0. So that's going to be our answer for this problem. And as you can see, they did the exact same thing, which is good. I wish they had some sort of let statement. So then x days, we will subtract a total of that. That's totally fine. So they defined x as the number of days, which is good. 3 times 4, and then they created the function here, right? Which is, or they created the equation here, sorry. And then therefore in 6 days, we will get 0. Sweet. This is a great solution, perfect solution, great analysis. Perfect solution and analysis. 2. Okay, so this is a really big one. I don't know why, but I think it's the formatting issue. So this is number 3. Number 3. So it says, are the 2 triangles below similar? And then it says here, it's multiple choice, right? There's A, yes, because the 2 pairs are of congruent yes, because there are 2 pairs of congruent corresponding angles. B is no, because there are not 2 pairs of congruent corresponding angles. Yes, because corresponding sides are proportional. No, because the corresponding sides are not proportional. So look at here. What we're looking here is that we have some sort of we have these 2 triangles, right? So let me draw these out. And again, this is a geometry question, or it could be a grade 9 kind of problem here. Okay, so we have this side is 14, this side is 10. We have this here is 65, this here is 30. And then we have a smaller one, but I'm not going to draw it to size, obviously, because I don't have space. This here is 7. This here is 30. And this here is 85. Okay, so the first thing we have to do is, so what we're going to do, I'm not going to look at the solution yet, but we're going to say, are these 2 triangles below similar? So again, take a moment. I'm going to define what similar is before you, and you can take a minute to work out this problem. Again, similar triangles. So first, we have to define what are similar triangles, right? So let's define what are similar triangles first, and then we have to define, okay, what about and if it fits this criteria, right? So again, what are similar triangles in this case? And think back to, again, congruence theorem. Think back to congruent sides and similar sides. What is the definition of similar triangles, right? Similar triangles, again, they are congruent, right? So they are congruent. Or the angles here are congruent. So they have the same angles, are congruent, but the side lengths are different in terms of that they're proportional, right? Angles are congruent, so they're the same, and the side lengths are proportional, right? Are proportional. So when we say that they're proportional, we have to say, oh, maybe one side is 2 and the other triangle is like 4 or something like that. So it's a factor of 2 or factor of 3 or factor of 4 or something like that. If it's like twice as big or 3 times as big, the side lengths are proportional, right? Okay, so we have that. That's fine. So can we define, so again, take 30 seconds to think about this problem here. So the trick here is to look at the angles first. So you have 65 and 30, and you have 30 and 85, right? So what I would do first is I would solve for this angle here first, because I have this is 30, this is 85, this here is 30, and this here is 65. Or what you could do is you could solve for this angle here, right? It doesn't matter, because what I want to do, I want to prove my first point here. Are angles congruent here? So I have to prove this here, and then it's this here, right? Okay, so let's do that. So we have this triangle. I'll say this is triangle A. Oh, sorry. This here is triangle A, and this here is triangle B. So in triangle A, again, if I want to find this all the interior angles of a triangle, what I have to do is I have to subtract it by the total, right? So again, angle or triangle A equals, again, it's 180 is the sum of all interior angles in a triangle, right? So 180 degrees minus, and you have 2 degrees here, right? Or actually, no, this is not a triangle A here. Sorry, my notation is bad. I'm gonna say that this here is x, okay? Define this as x, and this here is y, okay? So x here, or angle x, would equal 180, right? 180 is the sum of all the interior angles minus, and then I'm gonna have to add up these 2 angles, right? So again, minus 30, and then minus 65, right? So again, because I want to find what this angle here is, right? So I'm gonna have to subtract from 180 from both these numbers. So let's do that. So 180 minus 35 minus 65. I'm just gonna take out my calculator to do this. So 180 minus 30 minus 65 is going to give me 85 degrees, which means that this here, angle x, is 85 degrees. So I can write here, this is 85. This here is 85 degrees. And then let's look at angle B here. I'm going to solve for angle y here. So angle y says that it's also 180 degrees because it's still a triangle. It's minus, again, here is 30 degrees and 85 degrees, right? So 30 minus 85, and I should get 65 degrees in this case here. I'm just going to double check. 180 minus 30 minus 85 is 65 degrees. So I have here angle y is 65. So now I have to ask myself, are these 2 triangles congruent in terms of angles? And the answer is yes, right? Because why? I have here 30, 65, 85. I have 30, 65, 85, right? The triangle is just rotated differently, but I have the same angles here, which means my angles are congruent, which is great. Sweet. Angles are congruent, which means that let's see. Oh, this is angles and sides, right? So this angles are congruent, so that's good. And we have to talk about the sides here. Are side lengths proportional? So here I have a length of 14 and a length of 7, right? So again, this here it is proportional, right? Because I can say that this triangle A is double the triangle length of B, right? 14 is double 7, right? 7 times 2 equals 14. So the side lengths are proportional in this case. So in this case, I would say that they are similar triangles because here I would say that yes, because there are 2 pairs of congruent corresponding angles, because my angles here equal to this are the same angles in A as in B. So I'm going to say that A here is the correct answer, and they have here A is the correct answer as well. Okay, so again, I'm going to walk through the solution with you, and let's see what they wrote here. The students, again, from University of Waterloo. So it says here in triangle ABC, angle A is 30, 65, and 85 using triangle sum property. So that's what they did here. Again, they solved for 180 minus those 2 angles. and they did the same thing for this one. The angle y, I defined it. They solved for 65, which is great. Since two angles of the triangles are the same, therefore by the AA similarity rule, so the angle similarity rule, the two triangles are similar. That's true. Since all sides are not given, therefore there are no side rule that can be applied here. Therefore A is the correct answer. So I like this solution. So I'm gonna say great solution, but but I wish you included. I wish you included wish you included the step-by-step math for the triangle sum property. So again, when we talk about the math, it's just the 180 degrees minus the interior angles here. So I wish they included that, but it's totally fine. So I'm going to say the solution here is correct. Okay, so let's do this question here. This is number 4, right? This is number 4. Yeah, this is 3. This here is 4. Another geometry question here. So it says here, which undefined terms are needed to define parallel lines? So again, take a minute to think about this question. I'm going to repeat this again. Which undefined terms? So again, think back to my previous video. What are undefined terms and what are defined terms, right? So in geometry, remember this is in geometry. So again, undefined terms in geometry and defined terms. And we're asking the question, which undefined terms are needed to define parallel lines? So again, take a minute to think about this problem. If you have any questions in the chat, let me know. And what we're going to do is we're going to solve this problem together after a minute. So let's do that. So which undefined terms are needed to define parallel lines? Remember, undefined terms, I have 3 undefined terms, right? So maybe this will help you out. So undefined terms. So again, I have first is a point, a line, in a plane, right? Again, PLP is how I kind of think about this: point, line, plane, right? And these are all they're all undefined terms. Same with my multiple choice here: A, point and line; B is a line and a plane; C is coplanar and line; D is point and coplanar, right? So again, here they're all these are undefined terms here. So again, what does take about now 30 seconds to think about this question. What does which undefined terms are needed to define parallel lines? And if the term coplanar here just means it lies in the same plane. So if you're not familiar with that term, the term coplanar, it means lies in the same plane. The same plane. You could think of it as a co-captain or whatever, or cooperative, and then planar just means plane, right? So it lies in the same plane. So they're friends. So again, which undefined terms are defined parallel lines? So let's solve this problem together. So again, what are parallel lines here? Parallel lines here are lines here with the same slope, and they never intersect, right? So if you can think about in an XY coordinate kind of space here. So again, I have this. If this perfect line was straight and this perfect line here was straight here as well, these two, if they have the same slope, they're parallel lines. Which means they would never intersect with each other, and that's totally fine. They're same slope, parallel lines, they never intersect, right? So we talk about, which undefined terms are needed to define parallel lines? So again here, point is clearly, again, if I added a point here, a point does not mean anything here. I don't have a line here, right? So again, point here would not be the correct term, which means A and D are instantly incorrect here. So I'm looking at line, plane, and coplanar and plane and line, right? So again here, again, I have a line here. I need to have a line, obviously, to have parallel lines, so it's good. And then plane. So what is a plane here? Again, this here is XY plane, right? This here it's a 2-dimensional plane in this case. So what I can do is so basically my lines need to lie on the same plane for them to be parallel, right? Because if I had something like, if it didn't lie in the same plane. For example, if I had like a three-dimensional kind of shape here, and if I had something in the x-axis here, and then something going into the plane here, it'll intersect actually at some specific point, but it'll never be parallel. So they'll always intersect in this case, which means that they have to lie on the same plane. So again, plane here is correct as well. So again, it's down to B and C now. Line and plane are coplanar and line, right? So again, this here is a trick question. In the sense that coplanar here is not an undefined term. An undefined term just means that it's a point, a line, or a plane, right? Where all the terms are defined by. In the sense that coplanar here is actually a defined term, and it's defined by the definition of a plane, right? So in this case, B is the correct answer. Line and plane are the correct answer because line and plane are both undefined terms, and coplanar here is a defined term because it uses the definition of a plane, right? So there, B is the correct answer in this case, and they have B here, which is great. So it says here in geometry there are three undefined terms. That's what I said here. But for the perpendicular line, the undefined terms are point and lines, while the parallel lines are line and plane. Because by the definition of parallel lines, we know that the parallel lines are lines which are always the same distance apart, both lie in the same plane. So I don't really like this answer because it says the same distance apart. It should have said actually same slope. And because I really don't care about this distance here. This distance here does not mean anything to me. My lines could be so far away. Let's say like so far away, like maybe like this massive of a gap here, but there can still be parallel lines, right? So again, here I'm going to say good solution, but I think you meant that. Parallel lines have the same slope and both lie in the same plane. In the same plane here. So I'm going to say here is, or I'm going to say okay solution, but I'm thinking about that. So in this case, my right solution is incorrect because of this thing here, and I'm going to correct it and say, but I think you meant parallel lines have the same slope and both lie in the same plane. So I'm going to say here is incorrect. Okay. Next question here. This is question 5. Maybe need to speed it up a little bit. I'm at 10:30, so 10:32. So we're kind of on track here, which is great. So it says here 1 colon x, which actually means 1 over x here, equals x over 64 here. What number can replace x? Or what is x? Okay. Super cool. So what is x? So take a minute to think about this. Again, this is kind of a pre-algebra question in the sense that this is a proportion question, right? It's 1 over x, or I can say I need 1 cup of water for flour. So how many cups of water would I need for like if I had 8 cups of flour, 8 cups of water, how much flour would you need, right? So it's kind of a proportion question in that way. So you can look at this question. You can also think of this question as like a cross multiply kind of question, and that's what they did here. But we can isolate for variables and do all that stuff as well. So let's look at this problem, and let's take a minute to think about this problem. We'll solve it. So as here, 1 over x equals x over 64. Again, what is x? So in order for me to solve this question, I actually would agree with this solution, and we shall do the cross multiply that gives us this. So what it means when we do the cross multiply is that I make an x sort of shape here, and I'm going to multiply these two terms and these two terms together. So I'm going to group these two terms together, so they're going to make my left side, and then I'm going to group these two terms here, and they're going to make my right side here. So again, my blue is that x times x equals x squared, right? So x squared here, or maybe I'll draw it out for you here. So I'm going to do x times x. I'm going to do this in red for the right side equals, I have here, this is 1 times 64. 1 times 64. And then what I'm gonna just do this in black now because I don't really care about the sides here. I got x times x here is x squared, right? And then 1 times 64 is 64, right? Which is good. And now what we have to do is we have to isolate we have to solve for x, right? But I have this exponent here. I have exponent of 2 here, right? So in order for me to get rid of that exponent, I'm going to have to square root both sides, right? So if I square root this side and I square root this side, I'm left with x equals, these two things cancel out, and I have the root of 64, which means x will equal, what's the square root of 64 is plus or minus 8. And that's going to be our answer for this question here, plus or minus 8. So this here, they only put the positive solution, and that's okay. I would have liked it if they put the negative solution as well. But what we're going to have to do with this problem is we have to actually check it with the equation here. We're going to have to check for both the positive and the negative, right? So let's check. We're going to do a check in blue, let's say. So it's 1 over, in this case, I'm going to check for positive 8. So I'm going to do a check for positive 8, and this here would be a check for negative, right? So positive would mean I'm just subbing x into the equation here, which means I'm gonna have 1 over 8 equals 8 over 64, right? And so 8 over 64, I can reduce this fraction, right? 1 over 8 equals, I can divide both of these, the numerator and the denominator by 8, right? So if I do divide by 8, I'm gonna get 1, 8 divided by 8 is 1, 64 divided by 8 is 8, right? So again here, left side equals right side, which means my solution is correct for positive 8, right? But what about for negative 8? If I have 1 over negative 8 equals, I have here negative 8 over 64. So again here, what would my solution be, right? So let's look at this problem here. I can do the exact same thing and divide the numerator and the denominator by 8, right? So if I divide this side by 8 and divide by 8, I'm going to 1 over, this is negative 8, or I can say negative 1 over 8, right? Negative 1 over 8, doesn't matter where the negative goes. And then negative 8 divided by 8 here is negative 1 over 64. 64 divided by 8 is also 8, which means that left side also equals right side. So in this case, my solution here is actually plus or minus 8 is my solution here. Positive or negative 8. And in this case, the solution was only positive. So I'm going to say that the solution here is correct, but they forgot to, solution is missing negative 8. Negative 8 as its solution as well. Recall that if you square root a number, you must also verify, or it contains a positive and negative solution. We would also need to check both solutions to see if it works with the equation. So I'm gonna do that, and I'm gonna say solution is correct, but it's like missing something. So I'm gonna say solution is correct in this case because they're not wrong, right? They're just missing something here. That was 5. So I'm gonna do 6 here now. 6 here. So it says here, what are some examples of direct variation in real life? So what are some examples of direct variation? What are some examples of, and this is the term, direct variation in real life? So what are some direct examples, or some examples of direct variation in real life? So let's define this term first. What does direct variation mean? Direct variation, again, I have the solution here. It says direct variation is defined as two variables which increase or decrease at a constant rate. This constant rate is denoted as k. So this is a good solution in terms of that. It's a good mathematical expression because they're using this term k, which defines some sort of constant slope or constant increase or decrease. But I can also say, if it's a constant increase or constant rate of increase, of increase or decrease, and they denote it as this k term, then actually this is really ugly. Let me decrease. So what I can also say is I can also say that these two terms are proportional, right? They're proportional to each other, right? So again, constant rate of increase and decrease, again, just means that I'm increasing something at a constant rate or I'm decreasing something at a constant rate. So what would that mean in terms of a real life? What does that mean in real life? So they used, I'm going to see what example here. So it says here, they used examples of variation in life. Motorcycle with X covers distance Y an hour. Speed is increased and distance will be more in the same amount of time, right? So again, using this example of, I live Ontario in Toronto. So in terms of kilometers per hour. So I can say that if you're driving 60 kilometers per hour, it's saying that in one hour, I travel 60 kilometers, right? Which means you can say in 3 hours or something like that, I would travel, and I would just simply do 3 multiplied by 60 here, right? So to get 180 kilometers, right? That's the same thing. So it's proportional, right? In this case, I can write down 1/3 in this case. So this is hours by hours equals, again, 60 by 180, right? So again, this here is my proportion, right? Or another example of direct variation would be like adding like let's say 1 cup of water per 1 kilogram of flour or something like that. Flour. So if I had 3 cups, or let's say 5 cups of water, sorry, my writing is really bad, then I would have 5 kilograms of flour, right? So again, these here are directly variated or directly proportional, right? Because I got this factor 1 and 5 is I'm multiplying the thing by 5. Same here, I'm multiplying each side by 5. In this case, I was multiplying each side by 3 and this side by 3, right? So again, these things are directly they're proportional, but they're also they have direct variation. So again, this year's solution is correct, right? I only looked at the first one, but the solution is very, very good. So it says here what are some examples, and they gave an example here. I'm going to say perfect solution and analysis. Sweet. Okay, that was question 6, and let's move on to question 7 now. So it says here, which operation can we perform to find the number of milliseconds in a year? Milliseconds in a year. So let's take a minute to think about this. A millisecond in a year. So again, what is a millisecond in the first place? So I'm going to say 1 ms. Ms for millisecond. 1 ms equals, so millisecond equals how many actual seconds? A milli means the word 1,000, right? Think of millennium, 1,000 years. Think of that was a Christina Perri song, right? 1,000 years. Millennium, right? 1,000 years. A milli, right? A milli, Lil Wayne, is 1,000, right? There's 1,000 things or something like that. So in this case, there's 1,000 seconds, right? A millisecond would mean 1,000 seconds, right? 1,000 seconds. 1,000 seconds. And it's saying how many seconds, and it's like how many milliseconds in a year, right? So let's break this down. And I actually like the way they broke this down. Calculate milliseconds in a year. They broke out all the things, and then what they're doing is they're multiplying. So I actually really like the solution. So what we can do is we can do this. So in 1 year, I'm gonna have to multiply it by how many days in a year first, because that's our first kind of conversion here. In a day, we have 365 days, right? 365 days in 1 year, and then we're gonna multiply it by how many hours in a day, right? We have 24 hours in a day per day, right? This is, again, 1 year, 365 days per year, 24 hours per day. Not 24 days per day, that makes no sense. 24 hours per day, and then I have 1 hour, or sorry, how many minutes an hour? I have 60 minutes an hour. In 1 hour, I'm gonna have to extend this, minutes an hour, and then how many seconds in a minute? I have 60 seconds in a minute, right? And finally, how many milliseconds in a year? Milliseconds in a year. Sorry, how many milliseconds per second is 1,000, right? So I have to say multiplied by 1,000 ms for milliseconds per 1 second, right? Equals, because that's going to give us our question, right? So it says here, 1 year times 365 days per year, 24 hours per day, 60 minutes an hour, 60 seconds per minute, and then 1,000 milliseconds per second, right? So we're going to have to do, I'm taking my calculator, it's here, would be, let's see, 365, or I say 1 year, so 1 times 365 times 24 times 60 times 60 times 1,000, and I would get 3.15 times 10 to the 10 milliseconds in a year. So 3.1536 times 10 to the 10 milliseconds per year. And you're might asking, okay, how did I get this, right? I got this through this concept of dimensional analysis. So what I would do is I would, I have here, this is 1 year over 1 year, sorry. So years in this case, again, they cancel in terms of units. The days cancel in terms of units. The hours do as well. Minutes do. The seconds do as well. And I'm left with the numerator is just milliseconds, right? If you look here, it's just milliseconds. I crossed out this guy, this guy, this guy, this guy, this guy. I'm left with milliseconds, and my denominator is left with a year, right? So that's why I have milliseconds per year here. It's 3.1536 times 10 to the 10, right? Or I can also say it as this number here, right? Or whatever it would be. Let's see. If I have 3.15 million, I would have 3.15 billion milliseconds per year, and that's my answer for this question. And they have 3.1536 times 10 to the 10 milliseconds per year. That's good, which means this is a great solution and analysis. So that's how I would solve for this. I'm using this concept of dimensional analysis to cancel my units. You learn that kind of in higher level math. But this here, I'm stating all my units, right? I'm converting my units to make sure that my units here cancel out. So this here is correct. Okay, all right. Next question. This is question 8 now. 3 more questions left. Question 8. The sum of two prime numbers is 85. Sum of two prime numbers is 85. What is the product of two prime? What is the product of these two prime numbers? Is the product of prime numbers. Okay, sum of two prime numbers is 85. What is the product of these two prime numbers? So let's think about what a prime number is first before we solve this problem. What is a prime number? So again, a prime number here just means a number is defined as a prime number if the only factors are 1 and itself, right? So let's see, in this case, 1 is a prime number, 2 would be a prime number, 3. 4 would not be a prime number because I can divide that by 2. 3 I can only divide by 3. 5 would be the next prime number. And then 6 wouldn't be a prime number because it's divisible by 2. And then 7, and then 9 would actually be divisible by 3 here. So 10 wouldn't be a 1 as well, but 11 would, and so on and so forth. And as you can look at this pattern here, if you look at specifically this pattern, starting from 3 here, you can realize that I don't have any even numbers, right? Because if I have an even number, then it would be divisible by 2, right? Except for 2, because 2 is the only even number that's a prime number, right? Because if I had, for example, 64, it's an even number, I can always divide that by 2, right? Which means it does not qualify itself as a prime number. So in this case, my first kind of logic here is saying that can only 2 is the only even number that is a prime number. 2 is the only prime number that is even. Okay, sweet. And then what happens if I add 2 odd numbers together? So let's take, and these are all odd numbers, right? So if it took 3 plus 5 here, and we're talking about the sum, right? So it's x plus y equals 85, right? So I'm saying let x be the first number, let y be the second number here, right? So that's kind of my thing here. And if x and y were both odd, so if they're both odd, what result would I get, right? So again, if I have 3 plus 5, again, they're both odd numbers. If I add both of these numbers together, I would get 8, right? And that's an even number. If I added 5 and 7 together, I would get 12, which is also an even number. And 7 plus 11, both odd numbers, would give me 18, which is an even number. So we can say that our second rule is that if we adding 2 odd numbers would give us an even number, which means that my both numbers here cannot be odd, right? Because if it's odd, it would give me even number. And here at 85 is an odd number, right? Which means, okay, I have here x plus y equals 85, right? So in this case, both numbers can't be odd, which means one of my numbers, and the only odd number that's so the only even number is prime is 2, which means one of my numbers has to equal 2, right? So in this case, I'll say x 2 plus y equals 85, right? Which means my x here, therefore x equals 2, right? Just because if I added any other odd number in this case, it would add to an even, right? 1 plus 3 would equal 4, 1 plus 5 is 6, 1 plus 7 is 8, 1 plus 11 is 12, right? Again, this rule applies, right? So again, here which means therefore one of my numbers has to be 2. So 2 plus y equals 85. Now I have one, I only need to solve for one variable, right? So I have 2 plus y equals 85. I can move 2 to the other side here and say that y equals 85, and then I'm subtracting 2 from both sides, right? Minus 2, right? And then y would equal 83, which means my two numbers here are 2 and 83. And then I'd say asking our last, it says what is the product of these two prime numbers? So again, you can check if 83 is prime. I know that 83 is prime. The product of these two numbers, product of x, y would give me, so this would be 2 times 83, or sorry, let me write it here. 2 times 83, which equals 166, and that's going to be my answer for this problem here. And they have 166 as well. They use the same logic as I did, which is great. Only one number is prime. Only one even prime number is 2, and if we add 2 odd numbers, the result is even, right? So that's good. I'm going to say that this solution is good, great solution and logic, but I would use variables to help me identify what the two numbers would have been. Just because we're on this topic of algebra, we're more used to seeing variables here. That's what I would do. I would choose to use the variables here. Some say solutions, correct? 2 more questions left. Nice. So this here is a systems of linear inequalities question. This here is a little bit of grade 10 now. So say here, which system of linear inequalities has the point 3, 2 in its solution set? So it's saying it has the point 3, -2 in solution set, and we're given A, B, C, and D. So we have to actually verify all of these ones here, right? So let's look at A first. A here states that y here is less than -3, and y here is x has to be in between 2/3 of x minus 4. Not in between. Y just has to be less than this kind of function here. So let's see. And in this case, y is -2, right? So remember, this here is x, this here is y, right? Okay, so let's do let's use, I'm not going to say this is a, so let's do this one first. So let's verify that y belongs to here, right? So let's sub in our numbers. Y is -2, -2 is indeed less than -3, so that's good. It meets the first satisfaction here. And then y here is -2 again. And it has to be less than or equal to 2/3 times x here, which is 3 minus 4. Because -2 is less than or equal to 2/3 times 3 here is just simply 2 minus 4, right? And then -2 actually equals 2, right? 2 in this case. So that's okay. Let me just check my solution here first. -2 is this less than this here. -2 is greater, or here it says here -3 is greater than -2. This is actually wrong, right? Because I have here -3 is less than -2, not greater than, which means this here condition is wrong, which means A is not the correct answer. So I don't know why I wrote a check mark here. That's my fault. I think I got threw off by the negative sign. So sorry about that. So I checked A here. That's which is incorrect here. So A is incorrect. Let's do B now. So if A is incorrect here, I can look at the sign, right? So it's greater than, so I know A here is incorrect. I also know C is incorrect here by the same logic. So let's check B and D here. And B and D only has this switch in sign, right? And if you actually use logic in this case, if I know that this here, Y has to be less than -3, right? Because -3 here, right? Because -2 is less than -3, right? Or sorry, it's greater than -3. So that's fine, which means I'm looking for something like this, right? Which means I have B and D would be my answer for this one. And then for, because I solved for this linear system as well here, I have to say that instead of, this actually satisfied this equation here. So I'm looking for something like this in the red, right? Y has to be less than or equal to 2/3 x minus 4. So I'm looking for this guy here, are these two things here. Y here is greater than -3, and Y here is less than 2/3 minus 4, which means my only option here is, let's see, my option here is, I'm trying to think of what this is. -2, nope. Less than -2. So don't think that any of them are here. So that means I do have to solve for B and D actually in this case. So let me do that. Because I don't think any of these actually answer these questions here. So I'm solving for B, and then D here wouldn't be an answer. So it's actually I defaulted my answer to be, let's see. To be B here. And the reason why the answer is B here is because -2 equals 2, right? So in this case, I'm using using this condition here where it says that Y is equal to this. But basically, because I have here -2, these numbers don't change here, right? So again, I know that this here -2 equals -2. So all of these actually satisfy our Y variable. So we are only talking about this section here, and everything of these section here changes, right? So I'm looking for this specific condition here, which is B. So B here is my correct answer. So that's great. And this here, they plugged it in, so it's fine. And they actually did the same, they did the same logic as I did, and they only checked for this first condition here. So I'm gonna say here, perfect solution and good logic. Sweet. Okay, last question for today, right? Last question. I have 2 minutes to spare. Last question. So this is question 10. Maybe I'll go a little over time. So what is true regarding chords and diameter of the circle, right? What is true regarding chords and diameters of a circle? So again, if you look at my circle here, it's a really bad circle. Diameter is basically from the center. The diameter is a line segment. Oh, they actually gave me the oh, they didn't actually give me the answer here, but it's okay. We can answer this together. So we can say, again, a diameter here has, again, both chords and diameters have 2 endpoints, which is good. Diameter is a line segment that intersects the center of the circle. That's good, right? So again, the center of the circle matters a lot, right? The center of the circle means that, remember, this here is my, you can call this a radius, and 2 times my radius is my diameter, right? So this entire thing is my diameter, right? But a chord of a circle is different. A chord could encompass the center point, but it doesn't have to, right? Like I could do something like this. This would be a chord here, right? Or sorry, let me do this in blue. This here would be a chord, right? So it's not necessarily the diameter, so because it doesn't have to necessarily go through the center, right? So that's fine. So this here would be a chord. So that's fine. 2 is also correct. So 1 is correct, 2 is correct. Every diameter of a circle is a chord, but every chord is not the diameter. So let me read this again. Every diameter of a circle is a chord, but not every chord is the diameter. So this here is, so again, every diameter, so I have to read this out loud. Every diameter of a circle is a chord. Which is true, right? Every diameter is a chord, right? Because it goes through it. There's 2 endpoints, and it intersects some point, right? So the diameter here equals chord, which is good, but every chord is not the diameter, right? Because this here would not be the diameter of the circle. So 3 here is true as well. And it says here the diameter of a circle is double the radius of a circle, and that's what I did here. Right? 2 times r equals d, right? So that's here is correct, which means all 4 of these statements here are correct. So I'm gonna say all 4 of these statements here are correct. Good logic. So this here is number 10. This will be my final answer for this problem here. All 4 of these statements here are correct. Good logic. So this is awesome. So I'm going to say here a solution is correct. And that's going to be my video for today. So thank you so much for watching. Again, I'm going to again stream again in about an hour, and we're going to focus more on quadratics for that. So you get the grade 10 curriculum, or algebra 1, end of algebra 1 and algebra 2. So stay tuned for that. Again, thank you for watching for those of you home. And yeah, stay tuned for in about an hour to watch me stream again. So again, thanks for watching and have a great day.